Good afternoon, everyone. My name is Josh Fears. I am the campus director for CITRIS and the Bontow Institute at UC Merced. Welcome. Glad to have everyone here. I know we'll have other participants filtering in as I go through these introductory remarks. So thanks for your patience. This is the 13th year of the CITRIS Research Exchange Seminar Series. And 21 years with CITRIS being an organization within the University of California. It's one of the Institutes of Science and Innovation, if you didn't know that. We've long hosted a remarkable lineup of speakers on technology and innovation. Most of those have always been at Siddhartha Jidai Hall, and I've seen many of you there. Thank you for joining this talk, which is virtual, and we look forward to seeing you in person in the semesters to come. Today, we're joined by Ahmed Sabbir Arif. Ahmed is a assistant professor at UC Merced in the Department of Computer Science and Engineering, and he leads the Human-Computer Interaction Group at UCM. And his research focuses on making computer systems accessible to a wider range of users by developing intuitive and effective input and interaction techniques. A major thread of this work is focusing on a smarter solution for text entry, which I'm certainly intrigued by. But his other interests include mobile interaction, accessibility, and applied machine learning. After completing his doctorate work at York University, a postdoctoral fellowship at Ryerson, and receiving an NSERC ENGAGE Fellow at York, he went on to receive a prestigious Hellman Fellowship for junior faculty within the UC, 3 Michael A.J. Sweeney Awards on computer graphics and inputs, a CHISIG Lindgaard Award, among many things. So I'm very excited today to hear what he has to say about what if computers could read our lips, silent speech as an active mode of interaction with computer systems. Thank you, and it is my great pleasure to welcome Ahmed. It's all yours.
Thank you, Josh, for the beautiful introduction. Hello, everyone. Again, my name is Ahmed. I'm an assistant professor of computer science and engineering at UC Merced, where I joined in 2017 and established and now leading the Human-Computer Interaction Group. Today, I'll try to answer the question, what if computers could read our lips? In other words, whether it's possible to use silent speech as an active mode of interaction with computer systems. I have structured my talk into 3 parts. I'll start with an overview of the type of research my group does. Then I'll demonstrate the silent speech recognition model we developed in our laboratory. Finally, I'll conclude my talk with reflection on future direction for this research. The overarching goal of my research is to make computer systems accessible to everyone by developing intuitive, effective, and enjoyable input and interaction methods. My definition of computer is kind of broad. I consider everything that can process information a computer. And this includes desktop computers, mobile and wearable devices, virtual reality, automobiles, drones, or robots. In terms of human, I focus not only on young adults, but also elderly people, children, and people with various cognitive and motor disabilities. My research approach is to identify problems with existing interactive systems, then target those from theoretical and practical standpoints. In terms of theories, I mostly develop performance models to predict the performance of humans and computers and hybrid of human and computers. In applied domain, I develop novel input technologies, which requires prototyping and fabrication. And I also develop novel interaction techniques, which are mostly software and applied machine learning that are aimed at different computer systems and users. I brought a few example projects for demonstration. The first project demonstrates a novel two-thumb corded keyboard that enables blind people to enter text on mobile devices. The keyboard was developed in an iterative design process involving the representative user group As you can see that it places the keys at the bottom of the device based on later frequencies, and we also took account for anatomy of the thumbs for the user to use the bezel of the device as physical reference. To enter text with this method, users have to press multiple keys simultaneously, just like playing a chord on a piano to enter text. We conducted studies with blind individuals from Cove, which is an institute here in Merced for blind individuals. And the results of the study showed that blind people can enter text with our method about 32% faster than the method that are usually used on these devices. We also found out that users learn this technique quite fast. Only after a couple of sessions, they were able to achieve a good entry speed. Besides, they all wanted to keep using it on their mobile devices. The second project enables users to hold multilingual and polyglot conversation on mobile devices. Its aim was to break language barrier by enabling people to use their native language to hold a conversation. The system automatically translates language to users' preferred language so that they can hold conversation in their native tongue. In this video over there, you can see that two persons are having a conversation in their native language. One person is entering text in Mandarin, other person in Hindi, and they're having a coherent conversation. We conducted multiple studies to test the system, and we found out that this system, because it's all automated, it's about 35% faster than the default Google Translate on mobile devices. We also found out that the quality of the conversation was pretty good. Participants were satisfied with it, and they enjoyed the flow of conversation because they didn't have to constantly go back and forth between Google Translate and the text box. The third project develops a novel keyboard that arranges the QWERTY layout around the bezel of a smartwatch, divided into 7 zones to enable gesture typing. The purpose of this method was to enable or facilitate skill transfer between mobile devices and smartwatches. As you can see over there in the picture, the gestures that are drawn that were performed on smartwatches and smartphone keyboard are comparable. We used machine learning approaches to optimize the zones and the gestures. And those are also optimized for usability and to facilitate skill transfer between various devices. In a study, we found out that the technique is about 33% faster than the baseline and 56% more accurate. We also found out that it's possible to transfer skill between various devices when the keyboards are optimized for gesture similarities. The final example project is a fabrication project. We developed a digital thimble. As you can see in the video, this person is wearing a digital thimble that enables the person to enter text and perform various input actions in virtual reality. One of the problems we have in virtual reality is that you have to constantly hold these controllers, which kind of refrains you from using your hands to perform other tasks. With this thimble, you can perform freehand input in virtual reality without interrupting or refraining you from performing other tasks using your hands. The device uses optical sensor from a mouse to track the finger and a pressure sensor to detect touch and contact force. The components are packaged in 3D printed and fabric pieces and the cardboard case. As you can see that it's a very preliminary, very early stage of development. We haven't published any paper on that, but we tested the system in user studies and we found out that for input task, it yields about 22 to 27 words per minute with 0 to 5% error rate. for novice users who have never used this technique before. The reason the method is does not interfere with other tasks is because of the force sensors. The force sensors work like a trigger. You have to apply extra force for the device to activate tracking. With this, let's move on to the main topic of this talk. Before I do that, let's talk a little bit about text entry and why text entry research is important. We know that text entry has become ubiquitous. Nowadays, we enter text on various devices and in various settings. Yet there are several challenges that the research community must address. First of all, the most effective text entry techniques that we have are stationary. For instance, physical QWERTY keyboard. Techniques that are aimed at mobility, for instance, smartphones or smartwatches, have smaller screens. As a result, the input method often covers most of the display, as you can see over there in this picture. The keys are also too small for precise target selection. So if you're selecting targets because of fat finger syndrome, you're most probably going to misselect keys when in frequent text entry tasks. There are also no haptic feedback or spatial reference like the ones you get on your physical keyboard. As a result, these techniques are often slow and error prone, especially when you are entering text on the move. Speech is a more natural mode of interaction with computer system. However, numerous research showed that speech is unreliable in noisy places. It also compromises privacy and security in public places because the bystanders can hear what a person is saying, and the person may convey information that are sensitive. And it is not accessible to people with speech disorder because it relies exclusively on acoustic signals, which and people who have speech disorder represent about 8% of our population. Silent speech input, on the other hand, interprets users' lip, tongue, or vocal cord movements into text. It is a promising alternative to speech because of multiple reasons. One, it does not rely on acoustic signals. So in theory, it should be more accurate because the ambient noise will not affect performance. It must also be more private and secure because bystanders obviously cannot hear you because you're not actually vocalizing the words, you're just moving your lips. And finally, it's more accessible because it does not rely on acoustic signal. So people who have a speech disorder or cannot vocalize words could use this technique. However, there are several challenges with this technique. The first is the current methods, the current techniques we have are quite intrusive because they use implants or external devices such as sensors and trackers or specialized cameras around your head or inside your mouth, which are, as I said, not practical at this point. Second, the existing silent speech recognition models are slow and unreliable. So our solution to this is an image-based lip reading model that uses the front camera of a computer device to observe and interpret the movement of the lips. The reason we think that this could be a good solution because it does not require any additional hardware or sensors, and it's very difficult to find nowadays a computer system or tablet or desktop or mobile device without a front camera. So before we invest time on silent speech, we wanted to investigate its social acceptability. And the reason is that we have seen this many times in our field that an effective technique is not always accepted by users because they find it awkward in public places or find it unnatural. So an understanding of whether users are willing to accept the method socially or not is vital before we invest time on it. So for this, we conducted an online survey on Amazon Mechanical Turk with 71 participants. We had more participants, but after filtering and post-screening, we finalized with 71 participants to explore the social acceptance of both speech and silent speech input methods. Participants were asked to watch a set of video clips where users were using these two methods to interact with a mobile device in public and private places. So two examples here. Over there, this person is using speech in a private place, and this person is using silent speech in a public place. We then asked them to provide their feedback on social acceptance of these two methods from both users and observers' perspective. Just to clarify, users' perspective is that you're using the technique and how do you feel in public and private places. An observer's perspective is that you're observing someone else using the methods and how do you feel about it. The results were quite interesting. We found out that social acceptability for both methods from users and observers' perspective were significantly different across location. However, we did not find any significant difference between two methods across audience. Overall, in subjective feedback, participants expressed their interest in using silent speech input because it is more subtle and provides a high degree of privacy and security than the other methods. So to summarize, we found out that participants were more positive about silent speech input than speech because it was more subtle, more private and secure. And one of the factors that we did not actually consider before is that they do not want to disturb others. And many participants commented that in public places, they do not want to use speech because it might disturb the people around them. So the next step, we investigated users' anticipated performance of silent speech methods. So in the previous study, we found out that people are willing to accept it as an input method, but we do not know that what is the anticipated performance from this method. More specifically, we wanted to find out that whether their willingness to tolerate error in silent speech recognition is different from speech or not. For this, we conducted a Wizard of Oz study with 12 participants, where we injected 0, 5, 10, and 15, and 20% misrecognition errors. And these are examples of two methods. This is speech and this is silent speech. During the study, participants entered short English phrases using speech and silent speech at those 5 different injected error rates. We collected user responses upon completion of this study to find out that how much they're willing to anticipate or expect or to tolerate error in this methods. The results were kind of interesting. We found out that 0% and 5% error rates are the highest. There's no difference between 5%, 0 to 5% error rate. But we found out that when the error rate is 20%, there's no difference between the two techniques either. But interestingly, when the injected error rate was between 10 and 50%, users were willing to tolerate more errors with silent speech than speech. So as you can see over there, they were okay with having a bit more error with silent speech. And we investigated this further in qualitative, in a questionnaire, and we found out that they're willing to anticipate or tolerate more errors in silent speech to uphold their privacy and security. We conducted a series of other studies which we haven't published yet. We found out that people tend to speak slower when they're speaking or interacting with speech and silent speech methods. We also found out that the rate in which users speak is reliant on whether they're native or non-native speaker of the language. So in summary, we found out that users are willing to accept silent speech as an active input method on computer devices. And second, we found out that they're willing to tolerate more errors in silent speech than speech to uphold their privacy and security. This makes a strong case for developing a silent speech recognition model. So that's what we did next. So for this, we used LipNet as a base model. LipNet is a widely used end-to-end model for phrase-level lip reading that maps a variable length sequence of video frames to text. So it makes use of deep three-dimensional convolutional neural network, a recurrent network, and connection is temporal classification loss, followed by beam search, decoding, and a 5-gram character language model. We looked at different components of this model and found out that the 3D CNN neglects the hidden information between channel correlation in spatial and temporal directions, which limits the performance of the architecture. We also found out that the use of deep 3D CNN unnecessarily increases computational complexity and memory intensiveness. So we tried to address this in a revised and improved model, which we termed or named LipType, which combines a shallow 3D CNN and a deep 2D CNN integrated with squeeze and excitation block to capture both spatial and temporal information. We conducted an ablation study to find out that whether it works or not. And study revealed that this hybrid CNN overcomes 3D CNN's inability to address the information between channel correlation and the 2D CNN's inability to capture temporal information. We then tested the complete model, trained the complete model and tested it. We trained the model using GRID dataset, which is publicly available to download, which includes altogether more than 21,000 videos. And we picked about 7,000 videos for testing. For evaluation, we compared LipType with LipNet model. And in terms of dependent variables, we used these 3 metrics: word error rate, words per minute, and computation time. Results reveal that LipType, which is the improved model, outperformed LipNet in terms of word error rate. It showed about 47% reduction in error rate. It also increased improved performance in terms of word per minute. We found out that LipType improved entry speed by 39%. And it also reduced computation time by 9 seconds. So while we're going through the model, we go through the model here. So while we're going through various components of the models, we found some other limitations that were not addressed before. The first thing we observed is that silent speech recognizers do not perform well under poor lighting conditions. That's the first problem we identified. Second, we found out that these models tend to make various lexical and linguistic errors. So we decided to, so just an example here, over there, as you can see that there's some lexical and linguistic errors here because the quality of the videos were not good. So we developed an independent repair model that compensates for poor lighting conditions and corrects potential error in output using a custom language model. If you look at this model and compare with the previous structure, you'll see that we sandwiched the model with these 2 pre- and post-processing steps. So this is image enhancement, and this is a correction model that corrects any sort of language problems. The light enhancement network is an improved version of LipNet that takes a sequence of low light images and outputs enhanced images. For training, these enhanced images are compared with their corresponding normal light images to compute the loss, which is then backpropagated to fine-tune and optimize the model. We use LipNet because it demonstrated a much better performance with actual underexposed images compared to other models, both in terms of quality and computational complexity. The error correction module predicts and automatically corrects the potential recognition error made by the recognizer. It comprises of two submodules: an error minimization module that corrects potential error in recognized character sequence using deep denoising autodecoder, and a sequence decoder module that converts corrected character sequence to meaningful word sequences using spell checker and a custom language model. Just to summarize what's happening here is that we're sandwiching the model with a pre-processing and post-processing module. The first one is fixing the low light condition images, and the last one, the post-processing one, is correcting the language using an independent language model. And it is correcting the language in two different ways. First of all, it's correcting the characters, and when all the characters are being recognized, it's correcting the words and the sentence. We demonstrated its benefit in a user study, and for this we collected various popular speech and silent speech recognizers. Just to go back there, if you observe this one, the reason I was emphasizing on the pre and post processing is that these are independent of the recognition model, which means that in theory we can use this pre-processing and post-processing with any model. It doesn't have to be LipType. It should be, in theory, useful with any speech and silent speech model. So to test that theory, we conducted a study and we picked multiple speech and silent speech models. For speech, we collected these ones, as you can see, deep speech, and repaired deep speech is speech augmented with the post-processing model. Of course, we did not use pre-processing because speech does not rely on the video channel instead of only the acoustic channel. We use Kaldi and repaired Kaldi web to letters and repaired web to letters. For silent speech, we use LipNet and repaired LipNet, LipType, which is the improved version that we proposed, and repaired LipType, transformer, and repaired transformer. So these 6 pre-trained models were used in the study, where 12 participants collected, where we recruited 12 participants to collect data in diverse real-world conditions. For speech model, we collected data in indoor, outdoor, quiet, and noisy conditions. For silent speech, we collected data in dark, dusky, and daylighting condition. The rationale for that is for speech model, we found out that the models tend to make more mistakes in noisy conditions. And we wanted to find out that whether the independent repair model that we developed works with output that is contaminated with erroneous data due to noisy condition. For silent speech, on the other hand, we collected data in dark, dusky, and daylight condition because we observed that these models tend to make more lexical and grammatical mistake when those are taken in dark and dusky conditions. So we collected in 6 different conditions, diverse data set, and then we evaluated the impact of the repair model on each model's performance using the collected data. The results showed significant improvement in the performance of all speech and silent speech recognition model. Just to emphasize that we summarizing the results in the next slides. So we are not individually presenting the data for deep speech or repetitive speech or all individual models. Instead, we're averaging it for simplicity, but if you want individual data, you can always find it in the paper. So on average, speech models showed about 32% reduction in error rate and about 8% reduction in words per minute, and about 5.8-second increase in computation time. Silent speech model, on the other hand, showed about 57% reduction in error rate, about 10% reduction in words per minute, and about 7.9-second increase in computation time. So for both, speech and silent speech, the models improved entry speed. The model improved accuracy substantially, often over 50%. To summarize, we developed LipType, an optimized lip reading model for improved speed and accuracy. We then developed an independent repair model that processed video input for poor lighting conditions. We then conditions when applicable and corrects potential error in output for increased accuracy. We tested this model with various speech and silent speech recognition to demonstrate its effectiveness, and findings confirm that that the model can be used independently with various recognizers for substantially improved accuracy. So what would be the future direction of that? And I want to invest some time here because this is most important. So far, what we have done is that we have demonstrated that silent speech could be used as an active input on computer systems. And by active, I mean that people can actively use it to input text on various devices. And on computer systems with heavy processing power, we found out that it works pretty well, but the timing increases by about 7 to 8 seconds. Which means that we cannot use the model on mobile devices yet, because it's very unlikely that users will wait for 8 seconds to see the results of their silently spoken phrases. So our next step is to develop a model that works on mobile devices. This could be done in multiple ways. One of the strategies that we're following is to segment the video clips into smaller chunks and overlapping them so that we can identify the phonemes that are being spoken by the users, and then combine them to make them words and then phrases. We speculate that this is going to make the system usable on mobile devices. There are multiple applications of these devices. And I don't have results yet, but I can give you some examples that how we are using it in our laboratory. First of all, we are using it for surveillance. We are collecting video clips from web cameras and CCTVs, and we are trying to find out that whether our model could be used to identify what is being spoken when audio channels are not available. We are using it with automated user interfaces, and we're designing a driving simulator where users can use silent speech to interact with automobile devices interfaces. We speculate that this is going to make driving safer because people don't have to, or drivers don't have to perform action using their hands. or when they're using speech that may not always work, when there's music playing, or you have other passengers who are speaking or chatting in the car. So we have already started the project, and hopefully I can show some results in the future. We are testing it on virtual reality. The idea is that in virtual reality, when you're collaborating with other individuals, when you're speaking using audio channel, you cannot use speech to interact with the system because there will be interference and overlaps. One way to mitigate that is to allow people to interact with the computer system using silent speech, and then interact with the individuals you're collaborating with using speech. In that way, there'll be no interference, and both can be performed without any significant overlaps with each other. Finally, accessibility. As you remember, that I emphasize quite a lot on people who have speech disorder, but I have not tested, or we have not tested the technique with them, this population, and the reason being that our lab do not have access to this population. But we are trying to communicate with various institutions, and our hope is that in the future, we'll work with them to figure out that whether the model could be trained for them. One of the main challenge with people with speech disorder is that there are a wide range of disorders out there, and they don't compare with each other, which means that a person who has a specific type of speech disorder, his or her lip movements might not match another person who has a different speech disorder. So there's a chance that we have to train the system for individual speech disorders. But this is speculation at this point. We don't know yet. Hopefully in the future, we'll figure this out. Before I go, I'd like to thank my lab members, and I've been privileged to receive really talented students. This work, the works that I've presented and demonstrated would not be possible without their support and help and their dedication. So I thank them. I have quite a lot of projects on my website because my research program is interdisciplinary. My work spans over quite a lot of fields which are not discussed in this talk. But if you're interested, you can go to my website using this QR code and check out the video clips I have for various projects. And finally, I would like you to download the source code of LipType and play with it. You can download it and use it with various systems. I also have the data set available on my website. You can download it and train a different system if needed. One of the things that I'm encouraging everyone is to just add to the data set so that new models could be trained that could be more effective and useful. That's my talk, and I'll finish here, and I'm happy to take questions.
Thank you so much, Ahmed. It was great to have you, and we do have a few questions lined up. Before we jump into those, I guess, I was wondering if you could, think forward with respect to the technology and how elderly folks that are not digital natives, in fact, you may not even be using many digital devices whatsoever, and are also hearing impaired, what they might be able to expect in the future. As an example, my grandmother is quite hard of hearing, even though she has hearing aids, and she often reads my lips, and that helps her quite a bit. And so I really appreciated the direction that you're taking your work. The pandemic's been very hard for her, of course, because many of the medical professionals are masked up, and she has no sense of reference for that. Plus, she doesn't get the auditory. I guess I'm just wondering, what do you imagine the future may be for the elderly that have difficulty with human-computer interaction anyway, let alone some of these other challenges?
That's an excellent question. So I've been thinking about this for quite some time. Elderly people, I would say that oftentimes they are not open to adapting new technologies. So for that population, one approach could be using inactive, interaction, so passive interaction. So over here with silent speech, it's active. So you have to actively engage with computers. But if you have a system that can passively do that, for instance, if you have a computer system that can track your lips and can understand what you're hoping and just comply with that, that would be one approach to go about it. But in general, beyond lip reading, I think there are other ways to go about it, right? If you're asking about in general that how to interact with computer systems that are more natural and intuitive, I think it will be a combination of things. I don't think we'll have one answer to that. For instance, if you're going to a grocery and checking out with self-checkout, maybe silent speech would be an interesting option because you can give your PIN number or account number without violating privacy. But again, like when you're at home, maybe speech would be more appropriate because you don't have to be in front of the camera all the time. So I think the best choice for any sort of interaction is to make it invisible, so you don't have to think about it. So I like to take the example of Norman's the door example. That if a door is well designed, you don't even notice it. So I think that's the way we're going to go. It's going to be a combination of different modalities instead of one modality that works for all.
Yeah, thank you. A question from the audience. Tom is asking, I would imagine that some phonemes like fricatives are quite visible on the lips, but others, perhaps vowels, might be much less readable from the lips. Any comments?
That's accurate assumption. So some phonemes are easier to easier to recognize than some other phonemes, and that's why we have the repair mode. So the idea is that you have some gaps between the phonemes, and you try to guess that based on language and prediction model. One challenge, of course, that if you use something, if you say gibberish, like something that is not in the dictionary or the system, does not understand, those things are difficult to guess. I don't know what's the solution to that, but first thing first, we're just trying to fill in the gaps using language model, hoping or assuming that users are using proper English or whatever language you're focusing on. But yeah, I mean, his rights are that he or she is right that some phonemes are easier to guess than others.
We have two questions coming in from the watch party at UCM. I'll give them to you both. How fast would computational time have to be in order for it to be used on mobile devices? And then secondly, is it possible to train the model on an individual such that the LipType would be specific to that individual and perhaps that much more accurate?
Both are really interesting questions. The first one is a tricky thing. So we can actually use deception there. So this is one interesting thing with computer systems, that oftentimes actual speed does not matter. The perception of how fast a system is matters more. So if you look at speech, for instance, if you use Google Voice or some other speech technique, those are not really fast. But whenever you're speaking, you see the cursor moving and they're predicting one word or a couple of letters. That gives you the impression that it's fast. So if you ask me, I'll say that if you can guess or predict one word in about 2 to 3 seconds, that is going to be acceptable. But this is just a speculation from my side because you have to do an actual study to find out. But my speculation would be, one word in about 2 seconds to 3 seconds would be acceptable to users, providing that you're giving them constant feedback. But if you don't give them feedback, they have to wait for 2 seconds to see something. It's gonna, they're gonna perceive it as slower than it is, and they're not gonna use it. Yeah, it's a combination of actual time and perceived time. So we have to maintain a balance between these two. The second one is quite interesting because one of the things I was thinking at one point is that whether it's possible to come up with your own language. So if you train, you train the system to a person who is using lip movement, but not, because you're not supposed to produce sound, right? You're not producing or generating sound, so you don't have to be that precise. So is it going to be a unique identity or like something unique to that person or not? So this is something we have to explore later, but yeah, that's obviously a possibility, right? So one of the studies, so some of the studies we have conducted but haven't published. So I briefly mentioned them in the talk, but one of the studies we looked at that how people interact with these techniques. And we found out that when they're interacting with speech or silent speech, and when they know that the system is not good enough, like when they know that it's going to make mistake if you're not precise, they try to be precise. We human beings try to be precise and slower and more pronounced. We do those things because we want to help the system. But if we don't have to do that because the system is training to you, then what's going to happen is a different question. So this is an open question, but really interesting, question here. Thank you.
Yeah, and we have another question from the audience from Andres. Did you find that people tended to over-articulate when providing silent speech input? For example, more cardinal vowels than usual? And if so, do you think those people could find silent speech interfaces more cumbersome?
Yeah, we did see some traits there, in our studies. So in all of the studies, we recruited people who are native speaker of the language because we mostly focused on English. And we also recruited people who are not native speakers of the language. And we found out that users who are not native speakers of the language are, more cautious when they're entering text with speech and silent speech. They're more pronounced and articulated, and they're slower, and users who are native, they're like not as slow or articulated as non-native speakers. We also found out that it's all about their perception. So if they perceive that the technique is good enough, or if they perceive that the system will understand, then they let it go a little bit. So they're more relaxed about it. But if they have the perception, if they perceive the system to be not so accurate or not so reliable, then their behavior changes. I'm not sure did I give the right answer? Because does it?
Well, a follow-on question to that, it has my mind racing a little bit. I'm certainly not fluent in Spanish, but it's probably the second language that I know best. And I hear very distinct differences, regional dialects, throughout Latin America, certainly in South America and colleagues in Spain. Do you see more challenges like within languages as opposed to across languages when trying to incorporate silent speech?
Okay.
In the sense that, regional dialects for Spanish, for example, have very different pronunciations. And I'm just wondering if that is more of a challenge because it's the same language.
I don't know. My intuition tells me that most probably, within the same language, if you look at different dialects or different, accents, that would be more difficult to distinguish than different language. Because if the model is trained for, let's say, that English, and there's another model trained for Spanish, And if you're testing the system with individuals who speak the same way as the training data set, then I think it'll be easier than like having individuals who do not speak using the same dialect or accent. So it's all about, yeah. So there is a conflicting theory as well, right? I mean, so this is something we have to test to know. So I'm just speculating at this point, but my intuition tells me that it will be, if you're trying to distinguish, or if you're trying to find out that yes, because the language model that you're using, or the language model that you're using to fill in the gaps between the phonemes, they're likely to make more mistakes if you're using the same language but of different dialect. But if you're using a different language model for a different language, it would be easier. Am I making any sense, or no?
Oh yeah, I also want to make sure we get this last question in before things come to a close. Liz from the audience is saying a big percentage of your users will be the elderly who speak more slowly and cannot process mentally unless someone speaks slowly. Can you help them? I had so much trouble even understanding you, and reading the closed captions did not help. So I suspect between the the virtual world that we're in and in person, there may be some differences in the technology, but I think to the extent that you can use the technology to modulate both the speed and the accuracy for elderly users.
Yeah, that's a good solution. I think that's a good way to look about. Yeah, the system could be used to maybe make speaking more accessible to human conversation. I'm thinking about. So if you're having interaction with another person, and that person having trouble understanding you, maybe the system could be useful in that scenario. So yeah, so that's an important factor that I did not touch in this talk, but the system obviously could be used for human communication.
Yeah, that's fantastic. In one final thought here, there seems to be a trade-off between accessibility and most of your work is certainly making technology more accessible to others, especially those that may be blind or hard of hearing. But also privacy, and I'm thinking about just lip reading software that perhaps can take intimate details from individuals. How do you separate the positive application of your technology from the potential misuse?
Sorry, I missed the last part there.
The potential misuse of your technology, if someone were to be using silent speech as a means to get private details from someone's life.
Right. Yeah, that's a good question. I don't know. I don't have a solution to this, because I mentioned surveillance there, and it's possible to kind of use it offline. So you record someone speaking, and then kind of decode what the person said using the technique offline. And of course, there's a security and it's a security concern there. I don't have an answer for that. That's how to address that.
Yeah. I think that's the dilemma of our modern society. Thank you, Ahmed. Thank you, everyone, for joining today. It was a great pleasure. Again, no research exchange next week, but stay tuned for the final one of the semester. And the week following, Laurel Larson, UC Berkeley Department of Geography, talking about teleconnections in our watersheds. Thank you for joining today, and thank you, Ahmed, for joining us. Much appreciated.
Thank you. Bye-bye.